Yes. I have to figure out how to remove this banner at the end. No, I'm not able to remove this. Okay. So I will start today's lecture now. Yesterday, I left you all with the statement of an elementary lemma from which, properly speaking, belongs to a basic course in complex analysis. And I'm absolutely sure that most people attending this program would have seen one version of this lemma or the other. But the reason why I want to emphasize this lemma and give at least some details of its proof is because in this subject, especially when we study multiplicative functions, we often deal with Euler products and their properties very much. And, oftentimes you would like to make statements about products and you want a very handy lemma that covers practically all cases that you will meet to just quote directly a simple elementary lemma that relates products to sum. So the lemma that I have at least found very useful in many contexts is a lemma that I mentioned, is the lemma that I mentioned from Tenenbaum's book yesterday. And this covers practically all cases that one generally comes across when studying infinite products in analytic number theory or number theory in general. We should remember that the infinite products over primes appear absolutely naturally in various contexts in number theory because many objects or quantities are defined first by defining them for primes and then multiplying, combining them together to give the product and usually the quantity, and usually this is done by taking a product of the values, various numbers defined for prime numbers. So you need to be absolutely sure about, moving from product to sum, which I agree with you, it's a very basic mathematics topic. Nevertheless,
Yeah.
let us.
Surya.
Yes.
I have one small question.
Yes.
See, yes. You are assuming 1 plus un plus bn different from 0. Is it
yes.
real or?
Real meaning it's a complex number in general.
But you are writing the statement product converges.
Yes, converges. In C. I mean the partial products will converge to a number.
Okay. All right.
Yeah. So yeah, that's what I mean. When I say that this converges, it means that the partial products, namely the products of 1 to x of 1 plus un plus vn, these as x tends to infinity go to some complex.
Sir, so this will suffice. You can assume that 1 plus un plus vn, they are not 0 for sufficiently large n.
No. Yeah. Of course, you can remove finitely many terms always. No issue there. You don't want products. When we say they converge to something in C star. So when they go out, then when they tend to go out, then they die. Okay, so here is your lemma. So suppose h is a real number that is positive, and un and vn are just complex numbers for n greater than or equal to 1. So un, vn is actually a sequence of complex numbers. Okay, and you have the condition that u is in L2. So it's square summable. Un mod un square, this series converges, and vn is summable. Okay, so of course this means that vn is also also square sum up as after all, that's how things are when you sum over set. So the condition here is just that un is square summable and vn is summable, that is required. And then that the two sums, you just assume a common bound for the two sums by saying that the sum over un square plus vn in absolute values is less than equal to some h. So this real h comes in this assumption, and that the terms are distinct from zero. Then you want to say that this product is convergent if the sum is convergent. And Vn is always thought of as some sort of perturbation on Un. So the extra or the unnecessary part, so to speak, is your Vn. The part that we will focus on, we think of it as Un, and that part should be the one that really contributes to this product, and that should be square summable. So typically, when we look at applications, this 1 plus un plus vn itself will be an infinite series, where the first term will be 1, the second term we will think of as un, and the third term onwards, the sum will be vn. Okay.
So just a question. In your last lecture, you told that if f is a multiplicative function, then fp minus 1 by p is the up. So you were taking un is the same as defined earlier, or un is just any sequence?
No. This is an elementary lemma in about complex analysis. Okay, I'm going to apply it to the setting that we are interested in later.
Okay.
So this is just a statement about products and sum, nothing to do with analytic number theory at all. It's a general statement. What I'm saying is that there is this lemma, which is a general statement about product and sums, which helps us in various situations in analytic number theory. It's a very useful lemma to keep in mind. I mean, once you're familiar with this lemma, if you have any confusion about how products behave and how to go to sums from products, all of that is gotten rid of. Just use this, it will work. In most cases that we meet, practically all cases that we meet normally. Okay. So, for example, study of meromorphic functions, where things are defined by products and so on and so forth. All of that, whatever basic information you want is covered by this lemma. It's just a lemma in complex analysis. Ideally, it should not even be a part of these lectures, but since it's not so well known, I'm just emphasizing it here. Okay. So I hope the statement of the lemma is clear enough by now. You just assume that U is in L2, V is in L1. Their sum has a common bound. Their L2, the sum of UN square and Vn in absolute value. These sums that converge, they have a common bound H. Then my claim is that this converges if this converges. These are equivalent, actually. If this converges, the product converges. If the product converges, this sum of UN converges. So you can get rid of this extra part, and you only have to concentrate on the UN. And if the UN converges, then you're done. Okay. So how does one prove such a lemma? The proof is, of course, quite easy, but neatly presented by Terenbaum. So it's not difficult. So let us look at the proof just to tell you. In all such matters, it's
One more silly question, sir. Why you require that H? You will quantify something with that H?
Yeah. I have not used that H at all in the conclusion that I have stated, but I'll state another conclusion at the end of this proof. And for that I don't give the full proof, which is just 2 lines. I refer to the book, but that statement involves H. Okay. So I just, I'm using this H also within the proof. Which is the reason why I put the H. You really don't need the H if you only want the conclusion that I've stated. Okay. So you let E be the set of n's, indices n, for which the un plus vn in absolute value of un plus absolute value of bn is large. The sum of the 2 values is large, which is the natural set to look at. So if that set, if I know is finite, then I can throw away those terms and analyze the rest of the product. Right? So that would be the natural thing to do. If you look at the set of indices where the terms in 1 plus un plus vn in absolute value are large, you throw away that set from the indices. If that's a finite set, then you look at the rest of the product. If you can show that that converges, if the corresponding sum converges, then you are done, because you're only missing finitely many terms. Okay. So you must always remember that in infinite products and sums, you can always afford to throw away finitely many terms without affecting anything about the convergence of the thing, provided in the products case, yeah, you are not, I mean, those terms are not zero. So if you put back the zero, then you may have a problem, but otherwise you have no issue. Right. So first claim is that this set on which the mod un plus vn is large is a finite set. Why is that? That's simply a consequence of the way we assume the things. And in fact, it's probably, it's just very easy. So you see un plus vn should be greater than half. If that is the case, then un square plus vn will be greater than un square minus, I'm not reading the mods just for brevity. What I mean is mod un plus mod vn is greater than half. This implies that mod un square plus mod vn is greater than mod un square minus mod un plus half. Simply from this relation, you take minus mod un to the other side and you get this. Now, this is an expression which for all x, because for any real number, x square minus x plus half is x minus half the whole square plus a fourth, which is greater than 1 by 4, because this is always a positive quantity. So this expression here is always greater than 1/4 if mod un plus vn is greater than a half. So this un square, so the set of indices E on which mod un plus mod vn is greater than half satisfies this, namely that mod un square plus mod vn is greater than 1/4. So to bound the cardinality of E, you just have to use what in very, very basic probability they call the Chebyshev bound. This is not to be confused with Chebyshev bound for prime numbers. Chebyshev's inequality is what it's often called, and we use that. So you see on the set of indices where un plus vn in absolute value is greater than half, we have checked that mod un square plus vn is greater than 1/4. Therefore, the sum over this n belonging to this set of indices must be greater than 1 by 4 times the cardinality of the set. Right? Because each term here is greater than 1/4 on that set. Now, this sum you can extend to the full sum because these are all positive terms, and you can just replace this n belonging to E with n going from 1 to infinity, and that sum is exactly what we have called, what we have said to be less than equal to h. Therefore, you will get from this that the cardinality of E is less than 4 times h. So you have seen that E is plainly a finite set. So only for finitely many indices is it true that mod un plus mod vn is greater than equal to half. Of course, this is completely obvious, but you have a neat quantitative bound here that the cardinality of the set is less than equal to 4 times h, where h is the bound, common bound for the sums of mod un square and mod vn square from 1 to infinity. Okay, so since E is a finite set, to show our result, it's enough to show that you can drop the terms that belong to E, and then it's enough to show that the product 1 plus un plus vn converges if the sum of un converges. If you show this, then you're done. It's because you're only dropping finitely many terms. Now you use the standard. Now what is the advantage with working with the complement of E? The advantage is that your un plus vn, these complex numbers un plus vn, they not only belong to the unit circle, they in fact belong to the circle of radius half. Because E is the set on which this inequality is true, therefore for the n in the complement, it's less than half here, And that will mean that your un plus vn actually belongs to the disk of radius half, open disk of radius half in the complex. For complex numbers that lie within that disk, you have a logarithm, okay? And that logarithm is defined, so you have this log 1 plus, you have logarithm of 1 plus z, and that logarithm is defined by a series. It is this convergent series, right? And therefore, you can simply bound the difference between log 1 plus z minus z, which is just by taking triangle inequality, you get mod z square times half plus 1/3, and you can replace the remaining z's in this series by half because mod z is less than or equal to half. Now, the sum of this series is trivially less than or equal to 1, and therefore you see that for mod z less than half, less than equal to half, you have this nice inequality, which is completely, all numbers are specified. It's log 1 plus z minus z is less than mod z square. Okay, so once you have this inequality, what do? You just apply it to the terms of this product and sum and compare them. So you see that because for when n does not belong to E, this un plus vn lies inside this circle for which the logarithm inequality I just showed holds, and therefore log of 1 plus un plus vn minus un plus vn is less than or equal to mod of un plus vn the whole square, which by triangle inequality is less than mod un plus mod vn the whole square. Okay, so now mod un plus mod vn the whole square is less than or equal to mod of un plus vn square. There's a 2 missing here, so 2 times this you get, and you see that vn, since n does not belong to E, un plus vn, their absolute values are less than or equal to half, which means each vn and un in absolute value is less than equal to half. In particular, vn is less than 1. Therefore, vn square in absolute value is less than or equal to vn. So you see that this term is less than or equal to mod un square plus mod vn. Actually, there's a factor of 2 missing here, which you have to put. Okay, so mod un square plus mod vn whole square, mod un plus mod vn whole square is less than mod un square plus mod vn square plus 2 times mod un vn, which by arithmetic geometric mean is less than mod un square plus mod vn square. So totally you get a factor 2 here, and then you notice that vn is less than equal to 1, so this is less than 2 times mod un square plus mod vn. Okay, so having got this inequality, obtained this inequality, you just see that the tails of this sum, log of 1 plus un minus this un plus vn, that is less than or equal to this. And this full series we know is convergent. So if n and m go to infinity, this goes away to 0. Okay, and therefore this sum of logs converges to the same thing as this sum un plus vn. But vn we have assumed is in L1, so that part converges, and therefore you conclude that you see that sigma log 1 plus un plus vn converges is equivalent to un plus vn converging if n doesn't belong to E. But vn is already assumed to be in L1, so that converges. Therefore, this converging, namely sigma log 1 plus un plus vn converges, is equivalent just to sigma un converging as long as n doesn't belong to E. Okay. Now this log is defined on the numbers that we are looking at, and therefore this sum of logs is nothing but the product of 1 plus un plus vn, n not belonging to E, and we conclude that the product converging is equivalent to this sum converging. Okay, so this is typically how one proves this thing in elementary complex analysis, and that's basically the proof that I have written, just that everything is neatly worked out. And in fact, continuing with this proof and 2 additional lines which you can find in Tenenbaum's book, you see you obtain this bound. So you obtain the bound 1 plus, so you obtain the bound for the product, that the product 1 plus un plus vn is less than or equal to exponential 6 times h plus the sum of the real parts of un. Okay, this is the bound you have. Not only, so the convergence of the product depends on how the full series sigma un behaves. So this product will converge if sigma un behaves. But of course, just to, if you want to bound, then only the real parts of un come into the picture, and you have 6h plus real parts of un. Of course, the h contains the behavior of mod un square, but the bound that comes in is a real part of un here. Okay, so this is a neat explicit bound. So for the product, so product 1 plus un plus vn is less than exponential 6h plus the sum of the real parts of un. Of course, the behavior of un's, not just the real part, is contained within this h, which is a bound for sigma un mod square of sigma un and the sum of mod vn. Correct? So this can be obtained quite easily from whatever we have done using the standard inequality, which is 1 plus u is less than exponential u, valid for any real number u. Right? So this is this elementary lemma. Right? So if you've got the gist of the lemma, which just tells you how to pass from product to sums and backwards, then we can go and apply it to our situation. So application, this is what so this probably will answer what somebody asked me just a couple of minutes ago. So suppose you have a bounded arithmetical function, then the convergence of this product is equivalent to the convergence of this fp minus 1 by t. F can be just a bounded arithmetical function taking values, complex values, but being bounded. So why is this product and this sum convergence linked like this? It's again simply a straightforward application of this lemma. So you take 1 minus 1 by t times this sum. If you multiply out the terms, and you get that this thing is nothing but this series. This series converges absolutely because f is bounded. So you can rearrange the terms and rewrite this product as this series. Okay, so you see that 1 minus 1 by t times sigma f p power k by p power k. This thing can be written as 1 plus f p power k minus f p power k minus 1 by p power k, sum from k equal 1 to infinity. Now you put the contribution from k equal to 1 as up. Okay, u subscript p. So for each prime number p, the contribution from just that prime number, you put it, let's denote that by up, and the sum of the contributions from all other higher powers of this prime number we call b. Okay, so the sum of the contributions from all higher powers of this prime is called vp, and just the contribution from the prime is called u. Then you see that mod up square, if you take, because f is bounded, it's bounded by some bound b, let us say, then this is less than, maybe instead of b square, it should be b plus 1 the whole square times sigma 1 by p square. And that is a convergent thing. So up square, the sum of up square over all prime numbers is convergent. So up satisfies the condition of the lemma. Now, what about the sum of vp? So vp should be in L1. Now vp itself is a sum. Again, using the bound for f, you get 2b here, and then sigma over p power k, k going from 2 to infinity, that summed over all primes. And as you know very well, that particular sum is, so the just vp is bounded by 2b divided by p into p minus 1, and then the sum over all p is bounded by 1 by p into p minus 1. So sigma vp also converges, right? So that's a convergent sum. Thus, you have this is less than or equal to H, and therefore the lemma applies to tell you that this product converges whenever this sum converges. Okay, that's the reason why this sort of sums appear in Halash's theorem. I mean, it's just basically the part of this product which can possibly diverge. I mean, which really contributes to the product. That's the reason why it gets. Also, we have an upper bound like this. You see that the product 1 minus 1 by p is bounded by this sum, which is exponential 6h minus sum over the primes 1 minus real part of fp by p. So if this series, so you see if this series converges, you have a bound for this product. Okay, you have a bound for this product, and that is what is essentially used in Halash's theorem, and that's the reason why these series appear a lot. I mean, these series appear in the statement of Halash's theorem. So it's the real part of these numbers that matters in this bound. The H there is of course all bounded in terms of the bound for F itself, which is B. Okay. So I hope that with this, you are clear about how the sum of this series is related to this product. So whenever this thing converges, this series converges here, the product converges. So that's what one uses in order to conclude the theorem of Wirsing from Halasz. Okay, so here's the next step. So recall. Now going back to our Halasz theorem and Wirsing's theorem, the part of the elementary lemma we have settled. Now we go to Halasz theorem and Wirsing's theorem. So recall that F from n star to C is multiplicative. Then its mean value is defined as the limit of this ratio sigma Fn by x. If it exists, it's called the mean value of F. And the famous theorem of Halasz says that if F is multiplicative with mod F less than or equal to 1, okay, so F must be multiplicative, and in the, let me see. If F is multiplicative with absolute value less than or equal to 1 for all n in n star, okay, and if there is a real number tau such that this series converges, then as x tends to infinity, the partial sums of F behave in this fashion. They are asymptotic to, after division by x, these ratios, sigma Fn by x is asymptotic to x to the power I tau divided by 1 plus I tau, which is what, which is how the sum of just n to the power I tau behaves, times the product. So this product is what this function contributes. The function F contributes these partial products, which also depend on x. So notice that the right hand side is dependent on x. Moreover, if t tau is not 0, this is oscillatory, and therefore this limit will not exist in that case, and therefore the mean value doesn't exist. But we know precisely how the ratios of the partial sums by x behave if this series converges for a certain tau. Otherwise, if there is no such real number tau for which this series converges, so for all tau in the real on the real line, this series diverges, then the mean value exists, and in fact it is 0. Therefore, if this series diverges for all tau, that means that Fp and p to the power I tau are slightly far apart. So Fp doesn't go close to Fn as a function, doesn't go close to the function n to the I tau for any real number tau. In that case, if it is not close to any of the functions n to the I tau, then the mean value is actually 0. It exists and it is 0. So you have these two cases. Either the function behaves somewhat like n to the I tau, and that is quantified by saying this series converges. In that case, the behavior of the partial sums does mimic that of n tau. You have this part that comes from n tau, this part that comes from the function. Otherwise, the function doesn't behave like n to the I tau for any tau, and then the mean value is actually zero. This is Halash's theorem. Okay, good. So now, how did we deduce Wirsing's theorem from Halash's theorem? First of all, what is Wirsing's theorem? It says that if f is a real multiplicative function which is absolute value less than 1, then the mean value always exists and it's given by this product. This time it's an infinite product, not a partial product. It's the infinite product. And this product is taken to be 0 if it diverges. So the mean value becomes 0 if this product diverges. Otherwise, it's equal to this product. So any real multiplicative function whose values all lie in the interval -1 to 1 does have a mean value, and it is given by this product. And this particular product is taken to be 0. I mean, if it diverges, the product is taken to be 0. So the mean value actually is 0. Now, how do you deduce Wirsing's theorem from Halash's theorem? Just to recap the steps. If f is real valued and mod f is less than or equal to 1, then we showed that this series diverges for all tau that are not 0. The reason for that is that you only have to look at those primes for which the real part of p to the I tau is less than or equal to half. And those primes, since f has absolute value less than or equal to 1, this series is greater than or equal to half times the sum of the reciprocals of just those primes. The primes on which p to the minus I tau has real part less than or equal to half. That's just the cosine of the angle tau log p essentially. And you can determine the precise intervals the primes must lie in order that that cosine is less than or equal to half. And counting the primes in those intervals, we see that this sum of this series is actually divergent for whenever tau is not 0. So you crucially, of course, require that tau should not be 0. Otherwise, the angle tau log p will simply become 0. Right? So that's the only case where it could diverge or converge. I mean, that's the only case that's left. So Halash's theorem, if you look at this series diverges for all tau t in R t not equal to 0. So you're left only with the consideration of t equals 0. If for t equals 0, the series, which becomes this series, 1 minus fp by p, because f is real and tau is 0, you simply get 1 minus fp by p. Either it converges, in which case, according to this elementary lemma, this product converges. And if that is the case, then use Halash's theorem. And you see that by Halash's theorem, if this series converges, you have anyway sigma fn n less than or equal to x by x equal to this partial product, because tau is now 0. So the x to the power I tau becomes 1. 1 divided by 1 plus I tau also becomes 1. And you're left only with this partial product on the right-hand side of Halash's theorem's conclusion. And you know that this product converges because this series 1 minus fp by p converges. So you can set limit extending to infinity and you get the mean value to be this. Otherwise, this series diverges, in which case this product, in which case you have concluded that this particular series diverges for all tau in R, because we already showed that it diverges for all tau not equal to 0. If it also diverges for tau equals 0, it diverges for all tau in R. And just Halash's theorem tells you that the mean value of f exists and it's 0. So you have obtained Wirsing's theorem from Halash's theorem. So the conclusion of Wirsing's theorem is that if your multiplicative function is real and takes values in -1 to 1, then its mean value exists. It's given by a natural infinite product. It is this 1 minus 1 by p times sigma k equals 0 fp par k by p par k, that multiplied over all primes. This product is taken to be 0 if the product diverges, otherwise it's its value, and that is the mean value of x. Okay, so we have seen the statement of Halash's theorem, the simple fact that Halash's theorem implies Wirsing's theorem, and Wirsing's theorem, of course, contains P and T within it. This is an immediate conclusion from Wirsing, because P and T in the form pi x asymptotic to x over log x as x tends to infinity is equivalent to stating that sigma, the partial sums of the Mobius function behave like this, that if you take the averages, they go to 0. Now, if you apply Wirsing's theorem with f equal mu n, which is within its scope of application, you get that sigma 1 minus fp by p is, because mu p is minus 1, you will end up with 2 times sigma 1 by p, which diverges. So by Wirsing's theorem, you get that sigma mu n by, the partial sums of the Mobius function by x, that limit goes to 0, which is prime number theorem in this particular form. As strong, at least as strong as the prime number theorem, and Wirsing's theorem itself is contained in Halash's theorem, and it is Halash's theorem that we wish to. So now let us go to the first part of Halash's theorem. What are we going to prove in the first part of Halash's theorem? So we're going to show that if f is a multiplicative function which takes values less than or equal to 1 for all n in n star, and suppose that this particular series, 1 minus real part of fp, p to the minus I tau, this series diverges for all tau in R. Note that, of course, this series is a series of positive terms. We've been considering this series from the beginning of the lecture. This series is a series of positive terms. So when I say, so all I need is that for a good number of primes, this real part of fp divided by p to the I tau, this number is significantly away from 1. If that happens, then the sigma 1 by p will, then this series will diverge. If for a large set of prime numbers, this happens. So fp goes away from the function p to the I tau, for a good number of prime numbers, then this series will diverge. And if that happens for every tau, so fp somehow does not get close to any of these characters p to the I tau, any of these multiplicative functions n to the I tau, then in fact its partial sums on the average, meaning the average of the partial sums or the average of the values of f, namely the partial sum by x, goes to 0 as x goes to infinity. This is the first part of Halash's theorem. Then one considers what happens if there is a tau for which this series converges, and that's the second part of Halash's theorem. Now, the first part of Halash's theorem is the longest part. It will take several steps to get there. In fact, probably it will take me only one part of it I'll be able to cover in this lecture, another part in tomorrow's lecture, and probably I'll finish day after. So it's going to take a while. Naturally, one can ask if one can get shorter proofs and all that. This has been a subject of active research, and as I mentioned, the work of Soundarajan, Harper, and Granville in this context. But we'll stick to basically the classical proof, in which case we have a number of steps to do. So what is the first step in the proof of the first part of Halash's theorem? The first step is a passage to a mean. Okay, so what do we want to show? We are given an arithmetic function which satisfies these conditions, namely that f is a multiplicative function and its values are in the unit disk. Okay, and let us introduce the notation a of x for this 1 by x times sigma f. Okay, so let me write a of x for this, actually perhaps without the 1 by x. I may have made a mistake here. I probably don't need the 1 by x. So a of x is just the partial sum of fn. Okay, So now I want to show that a of x by x tends to 0 as x tends to infinity. So I want to study these limits. So first we'll show that a of x satisfies this inequality. Now, what is the purpose of this inequality? It is to relate a of x to its own mean value. When you can bound something, a function, by its own average value, in terms of its own average value, which is given by this integral, then you have a hope of showing that the function is small. You see, because if its value is less than its mean value, there's no way it can be big. It just gets iterative in some sense, and it will simply go to 0. So one hopes that one can show that the function is small, or ax by x goes to 0 as required if you can have such an inequality. Well, of course, it's not at all obvious how it works, but at least intuitively you get the feel that such an inequality may help. Okay, now for how to pass from that to the conclusion we require involves a good number of steps additionally. But let us have as our first goal to prove this particular inequality. Okay. Now you see, it so often happens in analytic number theory that the result is written in terms of some inequality which may or may not, on the face of it, make too much sense to you. But it's the idea behind the proof of the inequality that really carries the information. The actual inequality being whatever it is, we'll have to look at the principle behind the proof of this inequality. So the principle behind the proof of this inequality is a very important principle in the study of mean values of arithmetic functions. So let's see what the principle is. So here is the principle. Ax is the partial sum. So I claim that for any real number t greater than 0, at times log t is equal to sigma fn log n plus sigma fn log t by n. Why is that? At is by definition sigma fn n less than or equal to t. So I multiply log t, and therefore at times log t is nothing but fn summed from n to t, each term multiplied by the constant number log t. The point about log is that it satisfies this equation. I can introduce the n that corresponds to each term artificially. So log t is log n plus log t by n. Put that into every term. Otherwise, this log t is common and constant. You can remove it out and you get at log t. But I multiply it to each term, and for each term, I look at the n corresponding, and then I write log t as log n plus log t by n. Once I do this, I get this particular relation that I have marked as star. Okay, this relation is very simple. It relies on just the absolutely basic property of the logarithm, but it's a fundamental relation in the study of partial sums of multiplicative functions. Okay, so you might want to remember that everything starts with writing the partial sum, multiplying a log t to the whole sum, and taking the log t in, multiplying it to each term of the sum, and splitting that log t depending on the n corresponding to the term as log n plus log t by n, and getting two sums here. Okay, now let us first dispose of this second term fn log t by n. That's the easiest thing to deal with. Let us first dispose of the second sum. So to dispose of meaning, I just want to bound it. So I can say it's less than something that is not going to bother me later. So t is here, t was any real number greater than 0. But here I will now on assume that for a particular x, which I will fix later, t is less than or equal to 2x. Okay. Then I claim that fn log t by n is less than or equal to 2x. How does that work out? Because I have assumed that fn is less than or equal to 1, and log of t by n can be written as the integral n to t du by u, and the sum of log of t by n, n less than t, is equal to the sum n less than or equal to t integral n to t du by u. Interchange the sum and integral, you get integral part of u by u du, and this is a number. The integral part of u by u is less than or equal to 1. So you entirely get integral 1 to t du, which is t, less than or equal to t. And therefore you see that this, yeah? Yeah?
T greater than 1, you are assuming? Or?
No, you may assume that, yeah, you can take t greater than or equal to 1. Yeah.
That is better.
Yeah. Otherwise, you just get for x, whatever. I mean, otherwise it's trivial. Yeah.
Yeah.
T greater than or equal to 1, you can assume. In any case, it will be. Okay. So you get this bound, right? So so far everything is trivial. It's just of course, we use crucially, and you should notice the number of times we will use the fact that mod fn is less than or equal to 1. That's a very crucial assumption in Halasz's theorem. It's a bit of an annoying feature, and many people have worked on trying to remove that condition partially at least, and so on. But as far as Halasz's theorem is concerned, he uses this assumption that f is less than or equal to 1 repeatedly in absolute value. Okay, so with that you get rid of the second term. So we will not speak of the second term here anymore. It's just less than or equal to x, and it's in fact all that matters is less than some constant times x in absolute value. That's it, and that comes by just a trivial estimate that we make here. Yeah. Okay, so that takes care of the first term. Now comes the second term that we have to analyze. I'll get to the term itself, and this analysis of this term is where you put in the information that your function is multiplicative and that integers are formed by multiplying prime powers. Okay, this is where that information comes in. So that's the reason for introducing this log n into this partial sum in the first place. So I will use this notation. S will be the set of prime powers in all the slides that come after this. Capital S will denote the set of prime powers. So it consists of 2 square. It includes the primes, by the way. I mean, the primes and the prime powers. Okay, so it's just 2 square, 2 cube, so on, 3 square, etc. So all powers of primes except 0. So 1 is not a part of this, and I hope I don't make a mistake with 1 not being a part of it. Well, I suppose I don't, but anyway, because n equal to 1 features in these sums, so somewhere you might need something of the sort. Anyway, let's deal with that later. So now every number, every integer, factorizes uniquely as a product of prime powers. So you have this notation. You write n as a product of s is s double vertical line n means that s divides n and s is co-prime to n divided by s. So if you remove s out of n, then the remaining part does not have a prime number in common with s. This is the notation that we are using here. So s double line n means this thing. Therefore, the factorization of integers into prime powers can be written as log n is equal to the sum of s double line n, s belonging to prime powers log s. We'll put this into this thing. So we start with fn log n, which is the sum of fn log n, n less than or equal to t. We put in this prime factorization in terms of this sum. So this log n is now replaced by log s, s double line n, s belonging to the set of prime powers. So far so good. We have just replaced log n with its factorization, n with its factorization written additively using the logarithm. Now we make an interchange of summation. So if you interchange these two sums that are here, the conditions on S should be transported to the first sum. So that is S belongs to S, log of S then comes out, and the term that involves an n goes to the second sum. So Fn goes there, and the conditions on n have to be put below the second sum. Conditions on n are that n doesn't exceed t, and that in fact the S that is there here fully divides n, as in S divides n and S is co-prime to n by S. Okay, so that's what I've written here. Fn is equal to m times S, where m is now less than t by S and m is co-prime to S. So this is equal to this sum is equal to this sum. Log S is log S and S belongs to S. So this is just this rewritten like this. So now we've come to this third line. Now from the third to the fourth line, here is where we crucially use the multiplicativity of S. So now m and S are co-prime because m is nothing but n divided by S, and by assumption S divided n fully, so n and n by S with co-prime, S and n by S with co-prime. So you can use the fact that m and S are co-prime to split your f as f of S into f of n. And therefore your f of S comes out log S, that's written here. And what you get here is essentially the partial sum of f up to t by S. Okay, it's essentially the partial sum subject to a condition, which is that you are summing not over all integers up to t by S, but only those that are co-prime to S. Get it? So only those integers that are co-prime to S, and that's in the second sum, inner sum. Now, how do we deal with this annoying condition S co-prime to M? Well, we just do what is the obvious thing. The sum over all integers co-prime to M, co-prime to S is equal to the sum over all integers M, whether they're co-prime or not, minus the sum from those integers which share a prime divisor in common with S. But S is a power of a prime. So this notation Ks is that prime. So Ks simply means the prime whose power is S. So you just have to subtract out the contribution from the integers M, which are less than t by S, and divisible by that prime, the unique prime that divides S, because S is a prime power. Okay. Therefore, you have written this sum with this co-prime condition as the full sum minus the contribution from the integers which are divisible by the prime number that divides S. Now you put this all back into this thing, and when you do that, so we write Ks for if S is P power K, then Ks is P. Therefore, sigma Fn log n is log S Fs, is log S Fs, and here this Fm is now M up to T by S. So that's just A of T by S minus Fm, M now summed over integers up to T by S divisible by Ks. Okay. So this
Sir, there is a question in the chat box.
Now how do I do that?
So the question is, this is the same as Mobius inversion?
Which is the same as Mobius inversion?
I think Mayuk, you can unmute yourself and ask.
Can the person asking the question please?
Okay, his mic does not work. He's saying that removing condition when GCD is one condition. So you're handling the condition when GCD of S and M is one.
Yeah.
So you are subtracting with.
No, this is not Mobius inversion. I'm doing something very trivial. I'm saying that those numbers co-prime to S I have to sum over. That's the full sum, the sum over all numbers minus the numbers which are not co-prime to S.
Okay.
Okay. See, you have to take advantage of the fact that S is the power of a prime number. It's not some arbitrary number. It's the power of a prime. So there's a so the numbers that are co-prime to S are only those numbers which are not divisible by that prime. Okay. Okay. Not quite. I mean, it's just completely inclusion exclusion. I mean, the full set of numbers from 1 to T by S minus the contribution from those that share this prime divisor P, which divides S. That's all. So you just naively subtract out the remaining thing. There's nothing there except this. Okay. Right. Therefore, you get this highly important identity. Okay, I must, it's difficult to overemphasize the importance of this identity, which not only figures in Halasz theorem, it figures in a number of results. It's the starting point of a number of results on mean values of multiplicative functions. Remember, we didn't use, in this part of the analysis that we did not use anywhere the fact that F is bounded or any such thing. We only used the multiplicativity of F. We substituted log n in terms of sum of the logarithms of prime powers. We interchanged the sums and we rewrote the sums that appeared, and you got this identity. Okay, so this is an identity. It's not even an inequality. It's an identity. It's valid for all multiplicative F, and it is the first step in a method that has been extended. So Halasz has used it. Others have been. So this idea, I think, goes back to the work of Levin and Feinley, two Russian mathematicians, Soviet mathematicians from quite some time ago. Okay, so this is a fundamental kind of like very basic observation in the study of mean values of multiplicative functions. Okay, so now AX is this partial sum, and Fn is less than 1. Thus, AX has a trivial bound. It's less than or equal to integral part of X. So sigma log S F of, you see that this thing can easily be bounded like this. Okay, so I'm going to this first term, log S is there as it should be. Okay, so let me just try to bound the first term by triangle inequality. Just this first term, S in S, log S Fs At by S. If I apply the triangle inequality and I split the sum as coming from those elements, those prime powers which are actually primes, and the other prime powers which are squares and cubes of primes, etc., then you see the ones that are primes, I write the thing like this. So they will give me a term which is log P, F of P, mod F of P, but that's less than equal to 1, and then mod of A of T by P. So this is the contribution from the primes. If I remove the contribution, if I remove the term Fp as less than or equal to 1. Okay, so this is the contribution from primes. From the non-prime prime powers, so the genuine prime powers, those that are P square, P cube, etc., I simply trivially estimate everything. Okay, so A of T by S is simply less than or equal to integral part of T by S, and S itself is P power K for some K greater than or equal to 2 and some prime P. And then I get log P power K times integral part of T by P power K. All this summed over K greater than or equal to 2, P varying over all prime numbers in the range. Okay, so this is the estimate we have for the first sum that is there here. So I separate out the contribution from the primes, then the contribution from the prime squares. I estimate the contribution from the prime squares trivially, all the time using the fact that my multiplicative function F has absolute value less than or equal to 1. So that takes care of the first part. The second part is just trivially estimated. So the second part is easily done. Log S, F of S, this sigma Fm, m less than equal to T by S, with the additional restriction that this sum is only over those integers which are divisible by the unique prime that divides us. Okay, so you get here p par k, fs is less than equal to 1, and the sum, this f also I leave as less than equal to 1, and then I get m less than or equal to p by p par k, summed over only those which are multiples of p. But m is less than p by p par k, which are multiples of p, that's again bounded by integral part of this t by p par k plus 1 times logarithm p par k, and you have the sum over primes and sum over k greater than equal to 1. Now, how does one estimate this? It's completely trivial. Again, we take a trivial estimate, t by p par k, we replace the integral part with just the number, and t itself is less than 2x, and so you get k by p par k plus 1, k greater than equal to 1 log p. This double sum is a convergent series, k greater than equal to 1 log p times sum over all primes p. That's some constant, it's just fixed in nature. You don't, it has nothing to do with x or t or anything. You just, it's some constant, so you put that along with the 2, and you can finally write what you've got as at log t is less than or equal to sum over the primes in p of a t by p log p plus x for any type t, any real number t between, okay, if you wish, 1 and 2x, not 0 but 1 to 2x. Okay, so let me summarize what we have done so far. We started with this identity. So at was the partial sum sigma fn n up to x. We started with this identity, at log t equals sigma fn log n plus sigma fn log t by n. We used the second term was estimated trivially, okay, directly, and we said it's less than or equal to x, basically up to a constant, because f is less than or equal to 1. And then for the first term, we substituted this log n in terms of the prime factorization of n. This should be log s. I mean, I have written wrongly. We used n, not log n. N equals the product of s, s divide n. And then estimated trivially the contribution from the prime powers with k greater than or equal to 2, repeatedly using the fact that mod fn is less than equal to 1. So far we have reached this version, starting from this observation that we began with. We've obtained this. Our goal, however, is different. Our goal is to first prove this: ax is less than x over log x plus x over log x times this mean value times x log x by log x. So to proceed from what we have to this, it involves an averaging argument that you see in Professor Balasubramanian's lecture. He may have covered multiple averaging, or he's going to cover, either has covered it today or he'll cover it shortly, this idea of multiple averaging. Here we see as just an averaging argument, which, which very much kind of shares the principle of the multiple averaging, except there the key advantage is obtained by doing the averaging a multiple number of times. Here we do it only once. Okay, so to move from this sum, from the sum I showed you to this average, so to move from this inequality at log t less than the sum over primes of this plus x to the integral inequality that I have written here, ax less than this integral, is the next step, and that's done by average. Okay, so probably I will for today stop here, because this is new, meaning this is the second part, which I would prefer not to interrupt tomorrow. Okay, is that fine? What's the time?
Yes, sir. It's fine.
Yeah, okay. So you have any questions or anything to say?
If you have any question, please unmute yourself and ask. Otherwise, you can ask in the chat also.
Yeah, otherwise in the chat or anytime, or you can write to me. See, this these lecture little bit technical. I mean, quite technical it will be because they're detailed. So I'm trying to repeat the things again and again, just so that people get used to the details here. Okay,
Yes,
but
sir, yes,
it would be good if you are trying to learn this. It would be good to follow the lecture by copying simultaneously with pen and paper, as this, then you will be able to check it. I don't mind going slowly as long as, you know, if you feel that you want to learn the details as the lecture progresses, please feel free to stop me whenever, and also try to note down by hand as you see it on the screen. That would be my suggestion.
Yeah, I just covered multiple averaging today.
Oh, you covered it today. Yeah, that was the scheduled thing anyway. Yeah. So here we are going to use single averaging.
Single averaging.
Yeah. So it's also so it would give you another context. I have written here. We now average these things, so one can compare with Professor Balasubramanian's lecture. But there the advantage is gained out of doing it multiple times. That's the thing there. Here it's only a single average. Okay, so I will do this tomorrow, starting from this point. After recalling that we have already obtained this in the previous lecture, and then I will start from here and tell you how to get. Now start from trying to prove this. So the averaging technique, and then how to get this final version. Okay, so that's that.
want to ask something.
All right. Any comment? Any further comments? Anything to say?
Okay, so if there is no more questions, so we can thank the speaker for his nice talk.
Thank you. So see you tomorrow at 2:30.
Yes, see you tomorrow at 2:25. Yeah, so now there is a